Okay, this video is kind of a scaffolded one to help you understand this alternating series estimation theorem. And so what you have here is an infinite series, which we must assume converges, because otherwise you can't approximate its partial sum. So this converges to something, so I can even say that. And we want to use this finite series, or in other words, the first, I guess it would be the first four terms of the partial sum, and we want to use it to approximate. So I'm going to write the few terms out here just to make it clear. Right, so if n is a 0, then we get -1 over 1. And if n is a 1, we get +1 over 3 factorial. And then if n is a 2, we get a negative again, so we get -1 divided by 5 factorial. And then if n is a 3, we get plus 1 over 7 factorial. Okay, and so that's this is the last, or this is the first three terms, so we can call this like S3. I guess you call it S4, I guess, if you want to consider the first term, or the 0th term, the first term, but I'll just call it S3. So, so like what we see here is if we take let's take a little diagram here, right? So like, there's the limit. Here's, let's actually make 0, let's make 0 here, actually. So the first thing we do is we subtract, right? We're subtracting 1. And then we add 1, and then we subtract 1, and then we add 1. So, you know, when we add the first partial sum, so we must be, you know, the limit must be a negative number. If let's assume this is 0. If I subtract 1, I must have overshot, right? I must have overshot the limit. Okay, so like this would be that first term. And now I'm going to add the next term to the partial sum, so that should shoot me a little bit over. Okay, so that would be like plus my 1 over 3 factorial, and then if I from here minus, right, minus again, I'm minusing 1 over 5 factorial. Okay, I'm there, and then lastly I'm going to add 1 over 7 factorial, so like that would bring me here. So this is where S3 lands. Okay, and so we can tell now that a couple things. So again, this whole diagram isn't necessary to draw over and over. Notice I knew that because of the way these alternating series converge, and that the first term was a negative. I knew we had to overshoot it from the, you know, it must be, the limit must be a negative number, I guess is what I'm trying to say. So I had to start the diagram over there. Anyways, here's like, so this distance here, there's a couple of things we can notice. The last term in the partial sum, of course, is this, and that is positive. The value approximation is, so the value of the approximation in this case is greater than, okay, greater than the true sum. You can tell that from the diagram. But you don't need the diagram. We just know that since the last term is positive, then it's greater than the true limit. The error bound L minus S3. So just be careful. The error bound, this subtraction is the difference between the true and the estimate. And that would be a negative number in this case, right? Because we're subtracting a higher value from a lower value. So that would be negative. The limit minus, okay, the limit minus the approximation. Okay, and the partial sum approximation is an overestimate. Okay, S3 there is an overestimate. The last thing we did was add, so it's an overestimate. Okay, and then the last, so the error here, according to the theorem, is less than the absolute value of the next unused term, which I think we can tell would be this. Okay. Okay, so right, because if you look at the diagram, the next term is going to have to overshoot the limit. Right, the next term is going to overshoot the limit and like end up over here. We minus 1 over 9 factorial. Okay, and so if you do that in the calculator, you get, so rounded to the nearest, it says, I think here, 6 decimal places, that ends up being 0 point, and then there's 5 zeros and a 3. So that's not bad for, only 4 terms, and already you're within like the really tiny distance from the true limit. But anyway, that's the scaffolding. I kind of weave through the essence of the concept again, but hopefully that helps.